Hello, so in this video I'm going to take you through section 2 of the 2018 Higher Chemistry past paper. So question 1A is asking you what is meant by the term electronegativity. So this is just something you need to learn as a textbook definition, but it is an atom's attraction for bonding electrons. Then part 2, explain why electronegativity values decrease going down group 7. So because electronegativity is an atom's attraction for bonding electrons, that's all to do with how much nuclear charge the outer or bonding electrons are going to be experiencing. So if, because this question is asking about group 7, but it's the same for every group, if we take fluorine as an example, so fluorine's electron arrangement is 2, 7, and then chlorine's is 2, 8, 7. Okay, so as you go down a group, what's happening is you're getting more occupied energy levels. Now the bonding electrons are always the outer electrons. So if you've got more occupied energy levels, then you're going to have an increased shielding effect of the nuclear charge. So if you imagine the positive nuclear charge is in here, so that positive charge has got 2 layers of electrons between it and the bonding electron layer, whereas in fluorine the nuclear charge only has 1 other layer of electrons. So the reason that electronegativity values decrease is because of an increased shielding effect, so it makes it less attractive. The nuclear charge is less attractive to any bonding electrons because it's being more shielded. Okay. Question B. Explain fully why the boiling points of the halogen increase going down group 7. And you should name the intermolecular forces involved. So because the halogens are just elements, and they are diatomic elements, so they're covalent molecules, that means that they've only got LDFs, okay, because there's no difference in electronegativity because all the atoms are the same, so therefore you can't get permanent dipole, or hydrogen bonding. So in this question, you're basically looking at why the London dispersion forces get stronger going down a group. And the reason they get stronger is because there are more electrons. So if you have more electrons, you will have stronger London dispersion forces, because London dispersion forces are just a temporary uneven distribution of electrons around the atom. So the more electrons you have, the more likely you're going to get an uneven distribution. And if you do get an uneven distribution because there's more electrons, that partial charge that's established will be stronger. Okay, so in the answer to this, the boiling points increase going down the group because the London dispersion forces increase due to increasing numbers of electrons. So then, question 2A. Explain the decreases in atom size going across the period. So the atomic size decreases across period because you have an increasing nuclear charge, or you have more protons in the nucleus. So as you go across a group, you're not adding any extra layers of electrons, so there's no increased shielding effect. However, you are adding a proton each time you move across the period, which means you're going to have a stronger nuclear charge in the middle of the atom, which is going to pull the outer electrons closer and make the atom smaller. Then B part 1, circle the structure of the molecule above that contains bonds with the lowest polarity. So if it's a low polarity of bonds, and this is talking about bonds in the molecule, so these covalent bonds, for example. So we're basically looking to see which, if it's the lowest polarity, they want to have close to or the same electronegativity, because that means that they both have an equal attraction for the bonding electrons, and therefore it's not going to be very polar. So if we look up silicon's electronegativity 1.9, chlorine's is 3.0, so that's a difference of 1.1, and then phosphorus is 2.2 and 3.0 is a difference of 0.8. And sulfur is 2.5 and 3.0 gives you a difference of 0.5. So that means this molecule has the bonds with the lowest polarity. Okay, and then part 2, explain fully why of these three chlorides, silicon tetrachloride is the most soluble in hexane. So anything to do with solubility equates to like dissolves like. Hexane is polar. So what that means, sorry, it's not polar, it's non-polar. All hydrocarbon substances are non-polar. Okay, so you're looking to basically explain if, that this molecule is non-polar, because if it is the most soluble in hexane, it must be non-polar. So it actually has the most polar bonds in it, because that's the biggest electronegativity out of those three molecules. However, the tetrahedral shape, if I label the polarities on here, so the chlorines will be delta minus. So because this shape is tetrahedral, it's actually symmetrical, whereas all the other molecules are not symmetrical, they're asymmetrical. So these two molecules are polar. However, this molecule, silicon tetrachloride, is non-polar because it has a symmetrical tetrahedral shape. So the dipoles cancel out. Yeah. So like dissolves like. In these questions, it's important to talk about what all of the substances are, though. So you would say that for, the other two molecules are polar due to their asymmetrical shape, whereas silicon tetrachloride is non-polar due to its symmetrical shape. And hexane is non-polar, so silicon tetrachloride will dissolve in it. 2C part 1. Explain fully in terms of structure and bonding why silicon nitride has a high melting point. So it's got a melting point of above 1000 degrees and it doesn't conduct electricity. So if it doesn't conduct electricity, that means that when it's molten, that means it must have covalent bonding. The two types of covalent substances you get are covalent networks and covalent molecules. A covalent molecule is never going to have a melting point that high, so it must be a covalent network. And you should know that silicon naturally prefers to form network structures anyway. So because silicon nitride exists as a covalent network, it has a very high melting point because you have to break strong covalent bonds when it melts. Okay, so in a covalent network, you have to break the covalent bonds in it to melt it or boil it because there are no van der Waals forces. Whereas in a covalent molecule, you're breaking van der Waals forces, which are weaker than covalent bonds, so usually the melting point's a bit lower. C part 2, calculate the atom economy for silicon nitride. So the equation for atom economy can be found at the front of the data booklet. So it is mass of desired products over total mass of reactants. Times by 100. So atom economy basically tells you the percentage of atoms in the reactants that end up in your desired product. So we're looking for the atom economy of silicon nitride, which means the silicon nitride is our desired product. So there's only 1 mole of it because there's no number in front of here. So that means the total mass of silicon nitride is going to be 140.3. Then the total mass of reactants, we've got 3 moles of silicon chloride, so that'd be 3 times 170.1 plus 16 moles of ammonia, so that'd be 16 times 17 times 100. And then if you put that into your calculator, so you would get 140.3 over 782.3 times 100, which altogether gives you 17.9%. Okay, that's that one. So, right, dogs. Sorry about my dogs there. So, D part 1, complete the diagram to show the apparatus is suitable. So it gives you a little rundown of what's required in the paragraph. So if you read that, it will say that chlorine gas is produced by the reaction between hydrochloric acid and sodium hypochlorite. So that's what you've got in this bit here. And then the chlorine is passed over heated aluminium foil. So we need to have something that has heated aluminium foil in it. So usually it's easiest to draw kind of sideways tube. Just remember not to cut off the tubes that are carrying the gas through, because then the gas wouldn't be able to actually pass through the tubes. So you just need to make sure you don't cut them off. And then you can just draw what looks like some heated aluminium and just label it as heated aluminium foil. You can draw bits in if you want, but you wouldn't really need to as long as you label that the aluminium foil is heated. And then the hot aluminium chloride gas and unreacted chlorine gas are passed into a flask where the aluminium chloride cools to a fine white powder. So we need to put the gas into a flask. Again, just make sure you don't close up any of the tubes. And because we're cooling it, we want it to be in an ice bath. Yeah, and you would want to leave a little tube to let any extra chlorine gas out, just so that you don't end up exploding your funnel flask. It's quite hard to draw on this graph pad. So then part 2, explain why the aluminium foil needs to be heated at the start of the preparation despite the reaction being highly exothermic. And so you would need to heat the aluminium foil initially, because if it's not initially heated, then it won't turn the chlorine into aluminium fluoride gas. Okay, so it needs to be heated so that there's enough, basically the particles have sufficient energy at the start of the reaction. So 3A, describe a safe method of heating a flammable mixture. So that could be a heating mantle or a hot water bath, never a Bunsen for something that's flammable. And then B, suggest why there's a small test tube filled with cold water. So that would be to act as a condenser. So you may have seen like cold wet paper towel wrapped around the top, but a small test tube of cold water would do the same thing. So anything that involves cooling is used as a condenser. So then 3C, name product X. So the easiest way to identify missing products is to score out things that are on both sides. We've got C6H5. We've got COO. Oops, I need to get the H there. COO, COO. Then there's CH3, CH3. And then what we're left with is H and an OH, which makes H2O, so that would be water. Then part 2. So this is asking to explain why benzoic acid is the limiting reactant. And you need to include calculations in your answer. So you're having to do limiting excess calculation here. Let's clear up all my scrolls up there. So you've got 5 grams of benzoic acid. So write that there, and then the other reactant is methanol. So the number of moles you have of each, you'll need to calculate. So that would be N, M, and GFM. So the mass of benzoic acid you've got is 5 grams. The gram formula mass is 122. And then methanol, the mass is 2.5 grams you've got. And the GFM is 32 grams, which you get up here. You work out the number of moles of each, that's M over GFM, so 5 divided by 122 for the benzoic acid. So that's 0.04 moles. And for methanol, we've got 2.5 divided by 32, and that's 0.08 moles. Okay, now it's a 1-to-1 ratio because there's no numbers in front of them. So if you wanted to react all of the benzoic acid that you had, you would need 0.04 moles of methanol, but you have 0.08. So the methanol is in excess by 0.4. Oops. 0.04 moles, and the benzoic acid is limiting. Okay, but the reason why you would want it as the limiting reactant, it would either be to fully react all the benzoic acid, or it could be that the benzoic acid is a more expensive reactant, because you don't want to be adding excessive reactant that costs you lots of money and not reacting at all. Okay, so then part 3, calculate the cost of benzoic acid needed to make 100 grams of methyl benzoate. So we've got, the student produced 3.1 grams of methyl benzoate from 5 grams of benzoic acid. So 5 grams produced 3.1 grams. First of all, because we need to find the cost needed to make 100 grams of methyl benzoate, we're going to need to know how much benzoic acid we need first. So we're trying to make 100 grams of this methyl benzoate. So if we work back this way now, so we would have 5 divided by 3.1, because if we divide by the 3.1, that'll give us how much we would need for 1 gram, and then times by 100, which tells us how much we need for the 100 grams. So if you put that into your calculator, again, apologies for the dogs, that would be 161.3 grams. So the cost for 500 grams is 39.80. 1 gram would be 39.80 over 500, and then the 161.3 grams would be the 39.80 over 500 times by 161.3. So 39.8 divided by 500 times by 161. So that gives you 12. So that would be £12.84. So just make sure that you round correctly again, because it comes out as 12.839. Okay. So then question 4, draw a structural formula for a ketone that is an isomer of this aldehyde up here. So ketones have a carbonyl group in the middle of a carbon chain, so you could just draw pentanone, which is 5 carbons, because this is 1, 2, 3, 4, 5 carbons altogether. Or you could draw this molecule and move the carbonyl to here. It's up to you. You would obviously just add in all your hydrogens for this as well. Then B, name a reagent which could be used to distinguish between 3-methyl-butanol and a ketone. So that's distinguishing between an aldehyde and a ketone. So you could use Tollens reagent, you could use acidified dichromate, or you could use peeling solution. They would all give you a colour change if one was an aldehyde, but not the colour change if it was a ketone. And then name the strongest intermolecular force that occurs between these molecules. So they've got a carbonyl, which is does have a permanent dipole, but it's not hydrogen bonding because the hydrogen's not bonded to nitrogen, oxygen, or fluorine. So this would have permanent dipole interactions between them. Question 4D. Explain fully what can happen to 3-methyl-butanol that will cause the olive oil to develop an unpleasant taste. So it would become oxidized and form a carboxylic acid. Because it's an aldehyde, it would oxidize to be a carboxylic acid. So that would taste very nice. The other thing that can happen to fats and oils when they oxidize is that they become rancid. But because you're given the actual molecule, you can see it's turned into an acid. So then explain why step 1 is described as a condensation reaction. So a condensation reaction is where you have two small molecules joining to form a large molecule with the loss of water. Okay, so because you've got the joining of two molecules with loss of water, that constitutes a condensation reaction. And then naming product A, so it's got a carbonyl group in it, and the carbonyl's in the middle of a chain, which means it must be a ketone. So you find the longest chain of carbons, which is 1, 2, 3, 4, 5, 6, 7. Yep. And so that would be heptanone, but you have to tell me where the carbonyl group is. So it would be heptan 1, 2-one, because you number from the end closest to where the carbonyl is. Heptan 2-one so far. And then we've got this branch here, so that's got one carbon in it, which means it's a methyl branch. And it's on carbon 3, 4, 5, 6. So that'd be 6 methyl heptan 2-one. Then question 5, open-ended question about the relationship between fats, oils, detergents, soaps, and emulsions. So things you could speak about here are that fats and oils are esters made up of one glycerol molecule and 3 fatty acids. The difference between fats and oils is that the oils have unsaturated fatty acid chains, whereas the fats have saturated fatty acid chains. You could then talk about how that affects the melting and boiling point. So remember, the saturated chains have straight chains, which means they can pack, the molecules can pack neatly and have strong non-linear dispersion forces, which gives them a high melting point. Whereas the unsaturated chains in the oils, the double bonds cause kinks in the chains, which means the molecules can't pack as tightly, therefore they have weaker Lindner dispersion forces, so a lower melting point. You could talk about how they hydrolyze to form glycerol and 3 fatty acids. Detergents and soaps fall in there because in order to make soaps, you do carry out the alkaline hydrolysis of fats and oils to form sodium salts. You could then draw a picture of the structure of a soap where you've got the ionic carboxylate head and the hydrophobic hydrocarbon tail. Detergents are similar in structure. They have a hydrophilic part and hydrophobic part. However, they have a sulfonate head instead, which is more beneficial in areas of hard water because the sulfonate head does not form precipitate with calcium and magnesium ions. Emulsifiers work very similarly to detergents and soaps. So you could talk about the mechanism of soaps and detergents where the hydrophobic hydrocarbon tail burrows into the grease, the hydrophilic carboxylate head or sulfonate head, whether it's a detergent or soap, interacts with water, and when the mixture is agitated, they form micelle structures. It'd be a good idea to draw a wee picture at this point. And then those micelles can either remain suspended because their negative heads repel each other, or you can wash them away with your water. Emulsifiers work in the same way, but they are made by reacting edible oils with glycerol, which ends up with them having, again, a hydrophobic part and a hydrophilic part, and the hydrophobic part will interact with the oily phase. The hydrophilic part will act with the water-based phase, and you can agitate the mixture and create micelles, which will keep either the oil phase suspended in the water phase, or you can get it the opposite way as well. Okay, so there's loads to talk about in that. You can talk about how the fats and oils are formed by condensation reaction. We mentioned give the definition of a condensation reaction. Basically anything you can think of is chemistry related to these things. You wouldn't have to mention all of those things. Again, you get 3 marks for showing a good knowledge, 2 for reasonable, 1 for limited, 0 for none. So as long as you have maybe 2 or 3 different things you've explained fairly well, you should end up with 3 marks for this. Writing incorrect chemistry doesn't get your marks taken off, so if you think something might be right, just write it down and hope for the best, because you won't get marks taken off. It's not technically correct. So that's all I'm going to do in this video. If you want the second half of this paper, then you can find my other video on it. Thank you.